Hello. Good evening, dear all. We have completed the chapter number 1, and in every topic of the chapter number 1 in the videos, I have connected the concept of the theory to the numerical. But between the theory and numerical, there are formulas which are to be remembered so that you can have a correct numerical approach. This is Dhanu Saraiya with the channel Physics with Dhanu Saraiya. Please subscribe my channel and follow my channel so that you can actually come across the concepts which are taught very clearly to you, and you can attempt the CBSE as well as any entrance of a JEE or NEET or any other entrances whatsoever. Clear? Okay. So now let us start to understand what I am trying to do in this video. I am going to write down all the formulas and the theory with these formulas in short, so that it is a very quick revision of theory with the formulas, so that you are ready to approach for the numerical. So let's have a quick revision of both the concepts together. That is the theory and the formulas we can go through. Fine? Okay, so now let us start with the beginning of the chapter, where the name of the chapter is Part 1 Electrostatics, which is electric field and charges. Fine? Okay, so now first of all in the chapter we have the very first formula, that is charge. We had learned how to charge a body. After that we made a formula Q is equal to NE, where Q is the charge and N is a number and E is a charge on the electron, which is equal to 1.6 into 10 raised to minus 19 of a coulomb. This is the value which you have to by heart. Fine? Okay. Then when we came to the next concept, let me tell you that every concept is connected and related to other. Read it like a story. This is not a formula page. This is a formula page story in which every character is connected. Stories connect characters. Like that we will also connect the topic so that you remember the whole page like a story. And it is easier for to learn, remember and understand. Fine? Okay. So now Q is equal to NE, E is equal to the value given. When we have two charges, I am just writing two and charges, there will be definitely a force of attraction or repulsion between them depending on their polarity. If they are like charges, they will repel. If they are unlike charges, they will attract. Whether they are repelling or whether they are attracting, they are moving towards each other or away from each other. So for any motion in any body, whether it is a charge, we must have a force. What is that force? Between the charges, between the two charges, that is a Coulomb's law of forces. That formula for the Coulomb's law of forces is F is equal to K Q1 Q2 upon R square, where Q1 is the charge 1, Q2 is the charge 2. The distance between Q1 and Q2 is R. Fine? And K is also given. This force is between these two charges, where these charges are separated by a distance R. Okay, where K is equal to 1 upon 4 pi epsilon naught, where the value of K, which has to be kept in your mind, is 9 into 10 raised to 9 Newton meter square per Coulomb square. And epsilon naught is the permittivity in the free space, whose value has to be remembered as 8.854 Coulomb square per Newton meter square. What is the unit of this charge? Coulombs. What is the unit of this force? Newton. Any force will have the unit Newton. Fine. So this is the way you have to remember the concept, the formula, and very importantly units. If you don't write the unit in the exam, you are going to lose half of the mark from the whole answer. So result is very important. It has to be written correctly with the unit. Fine. Okay. So now from here where the charge are 2 and the force between the charges is given as the Coulomb's law, in this concept itself, we also had the force between multiple charges. That is, if at all we have more than 2 charges, then there would be forces between every charge on one single charge. Okay, so if I want to know the force on first charge, then it can be given as F12 plus F13, so on, and we add these forces individually with the help of vector formulas, that is the vector resultant, where F12 is force on charge 1 due to charge 2, F2 is force on charge 1 due to charge 3. We calculate them individually, add them vectorially by the superposition principle, which is taught to you in the videos. Fine. So we have come to the force between multiple charges. Clear? So let us box this formula so that we are clear what we are talking about. This is force between 2 charges. This is force between multiple charges available around a single charge. Fine. Okay. Now let us go to electric field. Now electric field is the Coulomb's law itself, but in the Coulomb's law, one of the charge is 1 Coulomb. Correct? So if one of the charge is 1 Coulomb, that is, if I say Q2 is equal to 1 Coulomb, then I get electric field. So we can write the formula of the electric field with its vector notation as the force itself, but in which one of the charge is 1 Coulomb. So it is just a force per unit charge. Another formula is also there for electric field. Remember, there can be multiple formulas for a single concept. So if there is a single concept with 2-3 formulas, you have to understand what is given to you, and according to that you have to apply the formula. So what is the another formula? K Q upon R square R cap. These are the 2 formulas of the electric field. Let us box these 2 formulas. Okay. Now this is the force per unit charge at a point due to one charge. Correct? So what can be the electric field due to multiple charges? I have many charges Q1, Q2, Q3, Qn. Then what is the electric field? Due to the availability of all these charges in free space. The formula for that electric field is E is equal to E1 plus E2 plus so on En, such that we add these individual electric fields due to individual charges Q1, Q2, so on Qn vectorially using the principle of superposition, and finally when we get the result, we add them vectorially using the parallelograms law of vector addition or triangular law of vector addition. These are the two methods of adding any vector we know from standard 11th. Okay, so now we have come to how to find out the electric field due to a single charge at one point, due to multiple charges at one point. That is this formula. Now let us consider a dipole. What is a dipole? Dipole is an arrangement in which there are two charges of different polarity. One is plus q, other is negative q, and the distance between these two charges is 2a. Okay, so this is a combination of two charges with a distance of 2a. That arrangement is called as a dipole. Now, what is the definition of this dipole is what I said just now, and what is the formula of this dipole moment that we shall write just now. P arrow, it's a vector product. Q cross 2a P cap, where P cap gives you the direction of the vector P, which is the dipole moment, and it is always, the direction of P cap is always from negative charge to the positive charge, which has to be remembered. Clear? Now, let us place this dipole in a situation where we want to calculate the direction or the formula of the electric field at a point which is on the axis of the dipole. P is here. So this is our dipole as seen, same dipole I have drawn, but I want to find out the electric field at the point P. Axial point this is called, because this point P is on its axis of the dipole. So I want to calculate the electric field at the point P, which is on the axis of the dipole. I want to find out its electric field at that point. So let us write down the formula for the electric field due to this dipole at a point P, which is on the axis of the dipole. Fine. And at a distance of r from the center. Fine. So what do we write the formula for that electric field? E is equal to 2kp vector upon r cube, where r is a distance from the center of the dipole to the point P. And also looking at the formula, you can understand that the direction of E and P vectors are the same because there is a positive symbol here. So now let us find out the electric field at a point on the equatorial plane. So let us draw the dipole again with a distance of 2a between them, and in the equatorial plane let us consider a point P which is at a distance of r from the center of the dipole. Then what is the formula of the electric field due to this dipole at a point P on the equatorial position of the dipole? The formula is E is equal to negative kp arrow on r cube, where the negative symbol indicates that the direction of the electric field and the dipole are opposite to each other. Fine. This also small points. Please remember, let us box these formulas so that they are in our remembrance as it is. Fine. Okay. Now, after understanding what is a dipole, what is the electric field due to a dipole at the axial point, what is the electric field due to a dipole at the equatorial point, let us place the dipole in uniform electric field. Okay, making an angle theta with the electric field itself. I have placed one dipole here. This is the direction of electric field. What is the meaning of uniform electric field? It means the value of electric field everywhere within this space is same. We have placed a dipole. Okay, then what is the force acting on this dipole? Is it having some value? Answer is no. F arrow is equal to 0. Is there any torque acting? Is the body rotating? Is the dipole rotating? Yes. How much is the dipole rotating? By a vector. Tau is equal to P cross E. Okay. So remember this formula also. What is it? Tau is equal to P cross E. That is the torque which will be observed by the uniform electric field. Okay, when you place a dipole in the uniform electric field. Fine. Okay. Now I'll just move from here so that whatever I have boxed in the yellow frame are our formulas which you have to remember with the small concepts so that it is easy for you to apply when a numerical is asked. Otherwise, concepts also you have to apply. Okay, so I will just move, take a pic of it, then we will go to the next page in the same video to complete the other formulas of the chapter. Fine? Take a pic. Now we go to a new topic of electric flux. What is electric flux? Electric flux is the number of electric field lines passing through an area. Suppose I have a plane here of certain area S. Let the area be S. Then electric flux is the number of lines passing through this particular area. Now this electric flux is depending on the angle between the area, plane and the direction of the electric field itself. Okay, that is what is electric flux. Okay, so if I change the direction from perpendicular to parallel to turn it, I will be changing my flux just like as if this is one frame and the water is flowing through the frame. Like that, this is a plane and the electric field lines are flowing through the plane. If I change the direction of the plane with respect to the board where the electric field lines are there, then theta will change. What is the direction of the area element? It is always perpendicular to the plane which we are considering through which the electric field is passing. Okay. So we write the formula of electric flux, symbol of electric flux is phi is equal to E arrow dot S. Arrow, where E is the electric field which is passing and S is the area of the plane through which it is passing, and theta is the angle between E and S. Okay, so this is the formula for flux. Let us box it. Let us come to the Gauss's law. From this flux we have derived the Gauss's law, which says us that the flux is equal to the charge enclosed in the Gaussian surface upon epsilon naught. So what is the Gaussian surface? The Gaussian surface is any surface with a regular or irregular shape, and if there are any charges with it, then We consider only the charges within the Gaussian surface and do not consider the charge which is outside. So we can even write it as Q net. Where is Q net? Q net is within the Gaussian surface which we consider. So flux is equal to Q net upon epsilon naught. That is the Gauss's law which is derived from this formula itself. Now let us write down the formulas of three concepts and use Gaussian law with these concepts on various objects. Fine. So first is the charge density. We have three kinds of charge density. That is linear charge density denoted by lambda is equal to Q upon the length which we are considering. Then we have the surface charge density which is denoted by sigma is equal to Q upon the surface area which we are considering. Then we have the volume charge density which is denoted by rho equal to Q upon volume, where V is the volume of the object which we are considering and Q is the charge. So this is called as linear charge density lambda, surface charge density sigma, volume charge density rho. Using these formulas, we shall apply Gauss's law to application 1, 2 and 3. Okay, first application of Gauss's law is a long wire which is uniformly charged. So it is a uniformly charged long wire for which we had considered a Gaussian surface which is cylindrical in shape. I am just drawing it for your remembrance. And the electric field which we have to find out is at a point P on the cylinder. Fine. The electric field which we found out was equal to E is equal to lambda upon 2 pi r epsilon naught n cap. Okay. Now where E is electric field at the point P, lambda is a linear charge density, r is the distance between the wire and the point P. Okay, distance between the wire and the point P. R is the distance between the wire and the point P. So the electric field which we get is what I have written just now. So let us box this also and remember these formulas as they are. Fine. Boxing on a page is very important so that those formulas are highlighted. Now n cap is the direction of the electric field, which is if lambda greater than 0, electric field is radially outwards from the wire. If lambda less than 0, electric field is radially inwards towards the wire. Okay. So if I have a uniformly long charged wire, uniformly charged long wire which is infinite in length, then the electric field is given by lambda upon 2 pi r epsilon naught. Fine. Now let us go to the application number 2, where I have a plain sheet which is again uniformly charged, whether positive or negative. Within that plain sheet, we can consider a portion which is uniformly charged, and through this portion it is not cut out, and through this portion we can consider a cylindrical Gaussian surface passing through that portion. Okay? Then the electric field due to this sheet is given by E is equal to sigma upon epsilon naught n cap, where sigma is the surface charge density of this plane sheet. Again, if sigma greater than 0, the electric field is radially outwards. If sigma less than 0, that means negative, electric field radially inwards towards the sheet. Fine? This also we shall put in a box. Fine? So if I have a sheet, place it anyhow like this or like this or like this or vertical or horizontal, the electric field due to this plane sheet is sigma upon epsilon naught n cap, where n cap is the direction of the electric field. Now we come to the application number 3 of Gauss's law, where we have taken a spherical shell. Now what is a spherical shell? It means it is a sphere which is hollow inside. In this shell or for this shell, let us consider 3 points. This is our shell. So 3 points, 1 point is outside the shell, 1 point is on the shell, 1 point is inside the shell with a distance r from the center. So let us consider the distance r from the center as capital R and the distance from the center to these points as a small r. Okay, so there are 3 conditions for which we find out the electric field. For r greater than 0, r greater than r, that means our point is outside the shell. The electric field is just like a normal electric field for a charge q, as if all the charge is concentrated at the center. Okay? For r equal to r, electric field is equal to kq upon capital R square. Okay? Where I have replaced small r by capital R square. Right? If r is less than less than capital R, that means the point which we are considering is inside the shell, then the electric field E is equal to 0 itself. So these 3 are the different points electric field. This is the electric field for a point outside the shell. This is the electric field for the point on the shell. This is the electric field if the point is inside the shell. Okay? So these 3 applications can be found out with the help of Gauss's law. Clear? So Gauss's law can be applied for various objects, out of which we have considered 3 objects: a wire, a plane sheet and a shell. Understood? Again, the direction of the electric field will be radially outwards if the surface charge density is greater than 0, inwards if surface charge density of the shell is less than 0, then the electric field radially inwards. Inwards. Okay. So this particular shell has a surface charge density of sigma. According to the value of sigma, the electric field will be pointed radially outwards or radially inwards. Fine? Okay. So I have mentioned the directions also for all the three of them, and the other formulas also I have boxed. So this is the way we can remember all the formulas of this chapter and revise the theory. When you revise the theory, you will be doing the formulas, and when you revise the formulas, you will be doing theory. Remember that. Okay. So now I shall again move, and you can take a pic of the whole page and memorize the formulas. Okay.